Hello everyone, welcome to the next part of our webinar series in which we will talk about interactive bridge design according to Eurocode. My name is Jaroslav Navratil. I work as the manager of the development team in the town of Brno, where we focus on numerical methods for the design and assessment of pre-stressed concrete structures. It's my pleasure to share my experience with you. Today, I will explain how to tune various design parameters to create the perfect design of a simple bridge structure according to Eurocode. At the beginning of the presentation, we describe the basic parameters of the structure to be designed, including the preliminary estimate of the pre-stressing level. Then, we refine the pre-stressing force in several steps. We perform the design of non-pre-stressed reinforcement, and then we advise on how to fine-tune the assessment of the stress limitation. Finally, we will show detailed check results, the design report, and last but not least, we will highlight the added value of Allplan Bridge design. Let us now briefly describe the design structure, which is simply supported single-span pedestrian bridge, and let us make a first estimate of the level of pre-stressing required. The footbridge is to span a length of 30 meters. The structure is designed as a pre-stressed concrete girder with a single solid T-section with haunches on flanges and on the web. What about the construction? The girder is cast on full span false work. Then at 8 days the supports are activated and the tendons are stressed. The cornice load is applied at 60 days, followed by railings at 100 days, which is also the beginning of the service. The end of service is assumed at 100 years. The live load represents the crowd of people either on the full width or only on 1/2 width of the pathway. The tasks for design and checks will be explained later. Code-based combinations are considered including the effects of creep and shrinkage. Standard material parameters are imported from the BIM+ database. Very important for the design are the parameters valid for the Eurocode bridge design, as you can see on the screen now. The level of pre-stressing is a key factor in the design of a girder. For that reason, we need to tune the tendon geometry and the number of tendons. Considering the simple beam, the geometry is clear, a parabola with a potential straight line in the middle. The pre-stressing force can be estimated by balancing the permanent loads. Assuming stress and forces in one tendon according to the first table, the minimum number of the tendons is 5. 5 tendons balance out 92% of the effects of cell weight, as you can see in the second table and in the bending moment diagram. The alternative way to make a preliminary design of pre-stressing is to keep linear stress due to characteristic permanent loads within reasonable limits. Usually it is required that the tendon is located in such a way that no tension occurs in the cross-section. This requirement will be met if the resultant of the internal forces is located inside of the cross-section kern. In order to calculate the linear stress by the design module, we need to input related tasks. Therefore, in the construction stages we have to define the so-called final stage. Then a new task, lean stress, is entered with the relevant load combination and the day on which the calculation is to be made. We have to specify if we want normal or principal stress and the result name. At the same time, we must specify on which part of the member the calculation is to be performed, the so-called assembly. So we select the beam and the start and the end of the stationing. It's also possible, but not necessary, to define the appropriate task to generate the associated report snippet with the desired assembly. Linear stresses seem to be within acceptable limits at the time of pre-stressing, which is at 8 days, minus 3.526, minus 5.5 megapascals, which we can see also here. A certain warning is suggested by the stresses at 100 years when almost 1 megapascal arises in the lower fibers. In spite of that, as the first estimate, we will assume one tendon group of 5 tendons. In the following part of the presentation, we will iterate to refine the pre-stressing force in several steps. The design must be satisfactory at all stages of construction and operation. Afterward, we will perform the design of non-pre-stressed reinforcement and then we will advise on how to fine-tune the assessment of the stress limitation. So we have completed a preliminary design of pre-stressing and we can test whether the structure will meet Eurocode requirements without non-pre-stressed reinforcement. In order to do that, we need to define the code check tasks. Similar to the case of the lean stress, we define the task again in the so-called final stage. On the Loads and Check tab, we launch the code check dialog box and specify the day on which the check is to be performed, the result name, the relevant load combinations, and the desired type of checks. For now, we'll skip the checks of fatigue and detailing. Again, we must specify the so-called assembly on which the check is to be performed. After we define the code check task for 8 days at the time of pre-stressing, we can run the structural analysis followed by the Eurocode-based checks. The results of the assessment can be plotted in the form of a 2D diagram where we draw the cross-section utilization in percents for each type of check, for example flexure, shear, torsion, along the length of the girder. At first glance, it is obvious that all checks are satisfactory, except for the brittle failure above the supports. Let's take a closer look at the unsatisfactory assessment. The leg of resistance to brittle failure is only at the ends of the girder. Here. Right-click in the 3D window will start the generation of the detailed check report for the brittle failure. By selecting the required section, the report is opened. It states that neither the brittle failure check according to provision 6.1 109 paragraph A nor paragraph B is satisfactory. Stress strain response prior to cracking shows the stress of 2.82 megapascals. As no soft reinforcement is defined, the brittle failure will appear in this section. But this does not bother us acutely, because we can design non-prestressed reinforcement that will resist the tensile stresses. So we don't have to deal with that now during the design of the pre-stressing. What about the check at 100 years? As a result of pre-stressing losses, the compression in the cross-section drops and the check of the ultimate resistance in flexure fails. This can also be illustrated in the interaction diagram here. As a consequence, even the capacity to resist the interaction of all internal forces cannot be sufficient. Therefore, the curve for the interaction in the figure showing the utilization is not plotted. Note that in the case of the flexure and the interaction, an additional non-prestressed reinforcement might help to resist the ultimate limit states, but anyway, for the same reason, the decompression condition fails, as you can see both from the 2D diagram and the stress state in the section at 100 years. The decompression condition requires the distance between the neutral axis and the closest tendon to be 100 millimeters in the direction to the compression zone. As you can see, the tendons are in the tensile zone. Therefore, we report a negative sign of the distance, and we put the utilization at 1000%. Note that the decompression condition is required instead of the limit for crack width for selected exposure classes XC4, XD1, XF3. I must point out that any amount of additional reinforcement cannot increase the compression reserve and thus ensure that the decompression condition is met. Therefore, the conclusion is that more pre-stressing is necessary. So, how much pre-stressing is needed? As explained above, pre-stressing can be designed by balancing the permanent loads. Assuming a simple parabola, we get the displayed formulas with required horizontal force H. The required force was calculated to balance the 0.8, 1.1, 1.0 and 1.2 multiplier of permanent loads. For a given number of tendons 5, 6, 7, 8 and 9, the achievable camber F of a parabola was determined depending on the location of tendons. For this camber and the required load balancing level K, the necessary pre-stressing force was determined. It is shown by the dotted lines here. This is compared in the graph with the force that can be deployed by a given number of tendons, which are shown by solid lines. It is recommended to balance 100% of the permanent load for so-called full pre-stressing, which is the pre-stressing when the compression reserve is required. Considering the pre-stressing force at 100 years, we need at least 7 tendons, as we can read from the graph. In the case of Eurocode, the decompression assessment at 100 years is governing in terms of designing sufficient pre-stressing force. It will therefore be sufficient to concentrate on whether the 7-tendon variant passes the decompression check. Utilization in terms of the decompression seems to be high, but the actual distance between the neutral axis and the closest tendon is 67 millimeters, while the required distance is only 100 millimeters. Thus, a small increase in pre-stressing force may ensure that the requirement is met. As we can see from the stress limitation check, the tensile stress in the tendon after anchoring can be increased by almost 3%. Therefore, we will increase the pre-stressing force by 2.5% in order to meet the decompression condition. After we increase the pre-stressing force, we obtain the distance in question equal to 126 millimeters and the utilization in terms of the decompression less than 80%. The condition is satisfactory. What about other code checks at infinite time? All code checks pass except the brittle failure above the supports. But again, as it has been explained, the brittle failure doesn't bother us acutely because we can design additional non-pre-stressed reinforcement that will resist the tension. Therefore, we don't have to deal with this problem now when designing the pre-stressing. A similar situation occurs at the beginning of the service. All checks are satisfactory, non-pre-stressed reinforcement will be designed later to avoid the brittle failure. However, the problem arises at the time of pre-stressing when there could not yet be a decrease in the pre-stressing force due to long-term losses. Therefore, the stress in the concrete under the quasi-permanent loads exceeds the limit, 118%. Let us investigate the situation in more detail. For that reason, we generated the report snippet related to the stress limitation check. As you can see, the compression in bottom fibers minus 1624 megapascals is too high compared to the limit minus 1377 megapascals. The limit is given by provision 7.2 paragraph 3 of the Eurocode, and it is 45% of the characteristic concrete strength. Note that the characteristic concrete strength at the age when the concrete is pre-stressed is 30.61 megapascals only. The stress limit of 45% FCK is applied to guarantee the linearity of concrete creep. As we calculated, the stress in bottom fibers at the time of pre-stressing does not comply with the required limits. What are the potential solutions to this problem? As you can see, there are many possibilities. Let's look at this in detail. As the reinforcement is part of the cross-section anyway, we can use it to release the concrete in compression. Therefore, we can add soft, non-pre-stressed reinforcement to the bottom fibers of the cross-section. However, the amount of the reinforcement can only be increased to a certain extent to satisfy the condition for maximum reinforcement ratio and to make the design economical. The second solution for the stress limitation problem is to reduce the scatter of prestressing. Possible variations in prestressing must be taken into account in the serviceability calculations. According to Eurocode, we have to check out two characteristic values of the prestressing force, supremum and infimum. Standard Eurocode recommends rather high values R sub equal 1.1 and R inf equal 0.9, which may lead to uneconomical design. At the same time, the Eurocode states that when direct measurements of prestressing are taken, then we can reduce its prestressing scatter. Considering the fact that both prestressing force and the tendon elongation at its stressing are measured, we can take R sub and R inf equal 1.0. Note that many countries decrease the scatter of the factors R sub, R inf in their national annexes. For example, Austria, Belgium, Netherlands and Singapore. The next solution for the stress limitation problem is to apply pre-stressing at a later age of concrete. As a result of hydration process, the strength and the modulus of elasticity of concrete increase with the growing age of concrete T. Eurocode provides the formulas for the mean concrete compressive strength at a certain age. As you can see, the strength increase is significant, especially at the early stages of the hardening. At the age of 8 days, the strength reaches only about 80% of the strength at 28 days and 2/3 of the strength at infinite. Therefore, postponing the application of the prestressing will help to increase the stress limit and may ensure that the stress limitation condition is met. In case of the aging accelerated by the increase in the temperature of concrete, we can input a fictive substitute age of concrete, which is increased compared to the real age. The same principle can be applied by sequential prestressing at two construction stages. We apply a small prestressing, 5 tendons only, at the time when concrete strength is low, and we increase the prestressing when the concrete strength reaches the required value. Let us recall that our problem is that the compression in bottom fibers at midspan is unacceptably high. However, the problem appears only at the time of prestressing, before the prestressing losses due to creep and shrinkage appear. If we apply a positive bending moment, which would stretch the bottom fibers, the stress limitation check may pass. Therefore, option to reduce the compression in the bottom fiber is to apply a ballast load temporarily. Of course, we can always increase the depth of the cross-section. However, this adjustment is often questionable because it increases the requirements for material consumption, increases the cost of the bridge, and degrades its aesthetic value. In addition, it is not always possible because it may unacceptably reduce the clearance height under the bridge. Let's try the first potential solution: to add soft reinforcement to bottom fibers to release the concrete in compression. Non-prestressed reinforcement is defined via reinforcement sets. Topologically, reinforcement set is a polygonal line which is orange in the picture. The line represents the cross-sectional area of bars, of one reinforcement layer distributed uniformly along the length of the line. There are three types of reinforcement sets in Allplan Bridge, which represent longitudinal reinforcement and stirrups resisting shear and torsion. It is assumed that torsional stirrups are closed with sufficient overlaps. Such stirrups can also effectively resist shear. The user can also select the option that longitudinal reinforcement is effective in transmitting tensile force caused by shear and torsion. The input of a reinforcement set is done in the tabs Structure and Cross-section. We select the input of longitudinal reinforcement, then the unit, and we fill in the property values, the name, the polygon represented by the boundary we have prepared the boundary for in this case, and the bar diameter and material. We want to have our reinforcement be effective not only for the flexure but also for shear and torsion, and we do not specify the amount of the reinforcement as we intend to let Allplan Bridge design the reinforcement automatically. The bars will be positioned from the beginning to the end of the polygon. After we define the reinforcement sets, we can run the design of the reinforcement area, which is necessary to resist the loads. The result is the area ASD. Apart from the design, the checks evaluate the stress-strain response and the utilization of the selected sections. For example, here the strength check passed with the utilization of 100%. The design tasks are defined just like the code check tasks, which I showed in the short video above. As the danger of brittle failure appeared in the sections at the ends of the girder, we performed the design for brittle failure only. Allplan Bridge calculated the feasible and economic reinforcement both in the bottom and top reinforcement layers in regions 2.5 meters from the ends of the beam. Let us investigate the necessary reinforcement amount for all types of checks except for the detailing rules. Again, we obtained an adequate reinforcement amount in design conditions both at the time of pre-stressing and at the end of the service. If you are interested in what part of the longitudinal reinforcement is necessary only to resist the tension from the shear force or from the torsion, we can perform a separate calculation in Allplan Bridge. As well as the longitudinal reinforcement, the program also calculates the transverse reinforcement required to resist the shear force and torsional moment. Let us recall the results of checks which we obtained with zero reinforcement areas when we tuned the pre-stressing force. The problem appeared at the time of pre-stressing when the utilization of the cross-section was 116% for brittle failure and 118% for stress limitation of concrete in compression. We will perform the checks now after we have specified the realistic but minimum required reinforcement. As we can see, additional non-pre-stressed reinforcement will resist the tension above the supports. That is why the brittle failure utilization dropped to 74%. That's okay. The reinforcement also released the concrete in compression a bit, but still the utilization of 117% is too high. Let's try to increase bottom reinforcement up to the maximum reasonable level. In Allplan Bridge, we can use the user-defined reinforcement with the variation of the reinforcement area. If we want the program to consider the profile 16 mm with a spacing of 80 mm at the midspan, we define a variation of the bottom reinforcement set area from 28.1 cm² to 20.1 cm² along the length of the girder. Compared to the case without the soft reinforcement, utilization dropped by almost 4%. But it is still not sufficient. We need some other way of fine-tuning our design. As explained before, the first natural option is to reduce the scatter of the values of pre-stressing force, supremum and infimum, for the checks at the time of pre-stressing. This can be done by modifying the design code parameters valid for Eurocode bridge design, which I showed at the beginning of my presentation. The results of the checks of all cross-sections at the time of pre-stressing after adjustment of the scatter of pre-stressing force show that the entire beam complies with EN requirements. It should be emphasized that the parameters R sup and R inf must be kept equal to the original values for the checks at any time other than the time of pre-stressing, because no direct measurements of pre-stressing are taken at the times. But that's okay, all checks at the beginning of the service and at 100 years are satisfactory with the original values of R sup and R inf. Having all ultimate and serviceability checks successful, we can run the last check of the detailing rules. Here I listed all checks of the detailing rules done with the design module of Allplan Bridge. The reinforcement, as defined during all the design steps above, satisfies all the checks except for the last one. The check of the maximum distance between bars according to provision 9.2.3 paragraph 4 is not satisfactory. But after we define 11 bars in top reinforcement set, all detailing rules are obeyed. At the end of our presentation, I will show the report, which is, after all, what a structural engineer sells. Finally, we highlight the added value of Allplan Bridge code-based design. Allplan Bridge allows to run the task check report in order to generate detailed report snippets in Microsoft Word. A separate snippet with governing results is generated for the flexure, shear and torsion, brittle failure, and interaction checks. Similarly, for SLS assessments, stress limitation check, crack width or decompression check, and detailing rules. Design code data report provides all relevant material parameters, models with assumptions taken from the codes, and parameters valid for the Eurocode, selected national annex or ASHTO code. Ladies and gentlemen, I hope that I showed you how to perform the design of pre-stressed girder in Allplan Bridge. The correct design is based primarily on the correct pre-stressing level. Only a certain partial issues can be fine-tuned with reinforcement. Aging, construction stages and rheological phenomena also play an important role. It is therefore necessary to understand the principles of structure mechanics and the methods prescribed by standards. Under these assumptions, the methods used in Allplan Bridge are an important aid in the design and assessment of the structure. The module helps to standardize the design procedure of your company. Therefore, it's less prone to misinterpretations of national standards and regulations. It helps the engineer to understand the sectional behavior and to perform safe and economical design. Finally, in combination with other Allplan programs, the module can verify the amount of reinforcement for reinforcement drawings, which makes the design tools complete. Dear ladies and gentlemen, I thank you for your attention and I wish all of us safe and beautiful bridges.